hopefully we'll have an exciting couple of minutes, up to 1 hour, and just a brief, that you know what is going to be covered today during this session. So I'll start with what are the available test methods, followed by fundamentals of partial discharge, that we all have a kind of a common platform, that we all know what we are talking about if you're talking about partial discharge. Then what is Tangens delta, what is the difference between Tangens delta and partial discharge. Then what is our equipment able to do for you, taking above diagnostics method into consideration, such as PD and Tangens delta. Then I would like to share some interesting information on some case studies where you clearly see the difference between different technologies. And to wrap today's session up, summary and conclusion. Of course, as always, we are very happy to answer your question afterwards. But as Ali has mentioned, we will also share a recorded file from the session, and you will also get the PDF. So if you get this PDF and have a later question on, we'll be very pleased to discuss those with you at the later stage. So what are the available test methods? You see here on the left-hand side we have different diagnostics methods, basically covering what we are discussing today. So first of all, partial discharge. Partial discharge is able to localize the weak spots within the circuit. That's one of the main advantages from partial discharge. If you go then on the right-hand side from partial discharge, we have so-called integral diagnostics method, and one of these integral diagnostic methods is Tangens delta. In contrary to partial discharge, Tangens delta will give you a value overall the circuit on the test. So Tan delta will give you an indication about the insulation from your total circuit, but will not be able to localize the weak spots. Then going further, on the very right-hand side, you see the test methods. First of all, 50 Hertz, which is very unlikely to be used because cable represents a highly capacitive load, and therefore straightforward 50 Hertz transformer is simply not applicable in regard to size and in regard to finance. Therefore, most of the manufacturers, in fact all of the cable manufacturers, using so-called resonance test set to test their cable after manufacturing. In field, we have the so-called VLF technology, which is either VLF sinusoidal waveform or VLF cosine rectangular. We'll go much more into detail later on during this presentation. And last but not least, there is also so-called oscillating wave shape, which is available to test your cables. Okay, what are the forms of maintenance? I mean, traditionally you see here on the left-hand side, we would have corrective after breakdown. That means you allow your cable to break down, and then you will activate your emergency team. They will go on site, try to find the cable fault as soon as possible, motivate the excavation team to excavate, then cable will be cut, will be rejoined together, and will be re-energized. Very traditional form of working. However, today you would like to see the weak point in your circuit before the circuit fails to work. And this is then done if you move to the right-hand side, preventive before breakdown, and here the lower field condition-based maintenance. If you analyze your most critical assets during their lifetime, you will be able to do a so-called condition-based maintenance. Means you will see the severity of the imperfection in the insulation, and you can advise your maintenance team to action before a breakdown. That's all about preventive maintenance and so-called condition-based maintenance. So some fundamentals of partial discharge. You see here we have the most common standards for partial discharge. There is on the one hand side a definition according to IEC 6270, and I would say IEC 6270 is the most commonly used standard in relation with partial discharge measurement. In this standard everything is described. There is a explanation of partial discharge, as well as there is an explanation in partial discharge in the IEEE 400.3-2006 standard. To simplify that and not only read what is written here, I always try to explain partial discharge as an imperfection in the insulation. So that's basically what partial discharge is about, and the technology allows you to find this imperfection before it comes to a fatal breakdown. Now, if we are talking about partial discharge, we also need to consider the type of the insulation, as various insulation materials tend to have a different acceptance level on partial discharge. I tried to highlight that at the very bottom part from this page. You see here sensitivity of partial discharge. Green means it has a rather low sensitivity on partial discharge, which is in particular air and mica, while oil, paper, SF6 and partly cast resin tend to have a medium sensitivity on partial discharge. And then if you move further right, high sensitivity on partial discharge has silicone and especially XLPE. XLPE is basically today's standard in regards to cable. So all new cable laid into the ground are basically XLPE, which is cross-linked polyethylene. From a dielectric properties point of view, a fantastic insulation, but very, very sensitive on partial discharge. So you will see that also later on during the presentation. Partial discharge is very, very much depending on the type of insulation. That's basically what I try to express here with this page. Okay, now let's go a bit further. What can be the cause for partial discharge? You see here just a few examples. These are all related to either PILC cable, which are paper oil impregnated cable, or they are related accessories like termination and joint. So you see here on the upper left hand side, if you have a dry spot, you know, where the oil is not nicely distributed throughout the whole insulation, this dry spot would clearly be seen as an elevated point for partial discharge, because the oil is here to insulate, and if the oil is not there, that would lead to higher amount or higher reading of partial discharge. The same is valid also for water ingress. Due to leach sheet corrosion, it would lead to a higher field stress. And if here the paper and layers are not nicely aligned, we will also see in this case then elevated amount of partial discharge. Again, or more causes for partial discharge, this time now instead of PILC cable, all related to XLP cable or their accessories. So you see here we have the very well-known water treeing problem. Water trees are not able to be detected by partial discharge. Fact is, because it's not conductive, therefore it cannot be measured with electrical measurements such as partial discharge. The water trees are there from the very beginning, and they grow throughout the period of 10-15 years without causing any problem. The further they grow, the closer they come either to the conductor or to the sheet, which will then convert them from water trees to electrical trees. Once they are converted to electrical trees, we are able to measure them with partial discharge. The disadvantages, remember it takes 10-15 years for a water tree to nicely grow without causing any problems. Once it converts to an electrical tree, it's a question of a couple of days until it leads to a bridge between conductor and sheet and therefore to a breakdown of this cable. So once it is converting, you need to be very, very lucky to be able to see those by performing just at that right timing a partial discharge test. Then further we have some impurities, protrusion of semicon layers, which we would be able to detect as partial discharge. Very common, the so-called voids, which is basically trapped air. And just imagine, you know, if the stress or electrical stress is high enough to bridge the two sides, you know, from A to B, we would be clearly see that as a partial discharge. Also mentioned here, especially water tree and voids, was a problem with the firstly introduced XLP cable. With today's modern type XLP cable, those water trees and voids have disappeared. Okay, as I have already explained with my previous comments, water tree does not generate PD only if they convert into electrical trees. If you do VLF testing on your cable, VLF which is seen as a pressure test on your cable, you would make these water trees to nicely grow during tests. And the aim of a VLF or pressure test is to break down the critical water tree during test, you know, that they do not break down afterwards. Now, electrically seen, what is the equivalent circuit diagram from partial discharge? Try to explain that here. So you will see capacitance A represents the healthy part of the insulation, while you have capacitor B, which represents the capacitance of the dielectric material in series with the capacitance of the imperfection, which in this case it's a cavity. You see here the capacitor C represents the capacitance from this imperfection in the insulation, and in series with capacitor B it represents then the total insulation from a capacitance point of view. Now, how do we detect partial discharge? If you have an ideal insulation without any partial discharge, you would have just a pure, nice sinusoidal wave without any peaks. So that would be a measurement without the appearance of any partial discharge. You see here, just try to classify very typical partial discharge to see how we can categorize them in the so-called phase-resolved PD pattern. So you see as an example corona in gas. You see here the pattern, if it is on the high voltage side, in the negative half cycle from the sinusoidal wave, and opposite if it is on ground. While we have here corona in oil, you see the typical corona pattern if it is on high potential on the negative half cycle, while you see the distinct corona pattern on the positive half cycle from the sinusoidal wave. Same is valid if the potential is on ground. It would just reverse what I have just said before. Then on the next thing, you have cavity and or surface discharge. You again see here the typical pattern. If it is on high voltage potential, you would have the distinct PD pattern here on the positive half cycle, and vice versa if the electrode is on ground. Normally, or as a rule of thumb, we can say that the factor of the distinct partial discharge is about factor 3 or higher than the corona. Now, a further example is a cavity which is completely surrounded by a dielectric. That would lead that you would have discharges at both polarities, so as well as in the positive half cycle, and same in the negative half cycle. And last but not least, here you have on sector A contact noise, where you see an indistinct noise pattern at the 0 points, so here at the beginning, medium of the half cycle, and at the end. And if you would have a floating potential, you would have no time consistent pattern. That means those patterns would be traveling along the sinusoidal waveform, and that would be a clear indication from a bad contacting of an electrode. To make it short, or to wrap this up, with this phase resolve PD pattern, we are able to identify the cause of the problem, because each partial discharge will draw a different PD pattern, and with this PD pattern it gives us a pretty good idea about the potential defect or the possible cause of this partial discharge problem. Just a second. Okay. Now, by talking about partial discharge, as soon as we start talking about, sooner or later we will use two main abbreviations. The one abbreviation we are using is PDIV. PDIV stands for partial discharge inception voltage. What does it mean? It means that this is the voltage level where the first measurable PD is seen on the measurement. What we normally do if we measure a cable voltage, we start with an applied test voltage of about 0.5 U0, and then we are slowly increasing in steps of 0.2 or 0.3 to 0.7 to 1 U0, 1.2, 1.4, and so on and so forth. And then the first time where we see a partial discharge, that voltage level will be indicated as inception voltage. Pretty much the same, but on the reverse side, it's the PDEV, which stands for partial discharge extension voltage. So for inception, we ramp the voltage up until we see the first partial discharge, and afterwards we will ramp the voltage down to see where the partial discharge extinguishes. That's very important, and I try to explain it a bit more in detail in the next two slides. So let me go to the first one. So you see here, here you see on this scale, this is U0, so means applied voltage. If we have an 11 kV cable circuit, 11 kV is the phase-to-phase voltage. If we divide it by the root of 3, we get the U0, which is in this case 6.4 kV, so that would be U0 here indicated with the black line. PD inception voltage would be indicated by the red line, so that would be the moment where we see the PD for the first time. Further down you see the blue line, which represents the extension voltage. So if we go now to see here, you may have some switching in your network, and that switching would generate some peaks. So eventually one of these peaks is big enough to trigger a partial discharge within your circuit. So what you want to see is as soon as the peak is gone, the PD is gone. And this is only the case if inception voltage and extension voltage are above U0. So if this is the case, you would see that this partial discharge here at the very low end of the scale is only active while that peak is here. As soon as the peak is gone, PD is gone. So in contrary to that, I try to explain it here. You see PDIV is well above U0, which is represented here by the black line, but in this case the extension voltage would be fairly below U0. So the effect from such a thing would be you have again switching process in your network which is generating peak. One of that peak is strong enough to trigger the partial discharge, but since the extension voltage is below U0, even though that peak is gone, the partial discharge would still be ongoing. And that's for sure something you would not like to see in your network, because it would mean that once the imperfection is ignited, it would constantly burn, and it would carbonize your insulation, and sooner or later your insulation is completely deteriorated, and then it would lead to a breakdown of this circuit. I have tried to explain it a bit more in detail here. So if you see here, now pulse is coming, triggering PD, pulse is gone, PD is gone. Fantastic, and that's what we would like to see. And then in contrary, again, the other side, PD is ignited by a switching process, pulse is gone, but PD is still active. So in short, to have a healthy cable, you need to see that the PD inception voltage as well as the PD extension voltage is nicely above U0, which is just the applied voltage. That's just in short an explanation about PDIV and PDEV. Now, we would like to show you some limits. These are just examples, but by measuring partial discharge in cables, as already mentioned earlier in this presentation, PD is not like PD. PD is very much related to the type of insulation. So if we have here the critical warning limit for XLP cable, you see here newly laid cable, we would like to see PD free until 2 times U0. In this case it's written 1.7, but doesn't really matter. So up to 1.7 we would like to see PD free. If you have an aged cable, you may see some partial discharge, but the critical amount of partial discharge in both joints and termination you would like to have below 1000 picocoulomb at U0. If it is above, you need to action. What do we recommend in regard to cycle of test? So if you have here a PD-free cable, which is PD-free up to 1.7 U0, we recommend to leave that cable for 10 years, no reason to redo it. However, there's always an exception to the rule. If you have very important cable, where you cannot allow them to fail, it is probably better. I wouldn't go to 1 to 2 years as written here, but I would like to 3 to 5 years to redo the test if these cables were found completely PD-free up to 1.7 U0. If you have an inception voltage between 1.3 and 1.7 U0, we would advise you to repeat the test after 3 to 5 years. If you have a PD inception voltage above U0 up to 1.3 U0, we would recommend you to redo the test every 2 to 3 years. And if you have a PD inception voltage below U0, we would advise you to redo the test every year, especially here if you have partial discharge at the time you energize the cable. We advise you to redo it every year to see the trend from the partial discharge. As long as it goes nicely and steadily up every year, it's all okay. But as soon as you see a stiff increase of partial discharge in this particular circuit, then it would be time to action. Now, in contrary to that decision making for PILC cable, you immediately see, while we have had 1000 picocoulomb here on accessories for XLP cable, we have here 10 times more for oil-filled joint and 10 times more on oil-filled termination. Remember when I said that PD is very much related to the type of insulation? You see here a clear picture that I mentioned that PILC cable is much more tolerant on partial discharge than XLP cables are. So here about the same decision-making matrix. If your cable is PD-free up to 1.7 U0, we advise you to redo the test after 5 to 10 years. If you have inception voltage between 1.3 and 1.7 U0, we advise you to do it within the next 5 years. And then if you have an inception voltage around U0 and 1.3, 2 to 3 years. And if your inception voltage is at rated voltage or below, with an amount of lesser than 5000 picocoulomb or 5 nanocoulombs, then again redo it after 2 to 3 years. If your amount of partial discharge is above 5 nanocoulomb, then we would advise you to do it annually, just to see the trend, how far or how fast is the PD activity increasing in this particular circuit. Here another decision-making matrix. So here you have the condition of the cable on the left-hand side. On the right-hand side you have the importance of the circuit. So if you have a circuit which is in perfect condition, no PD at all, up to 1.7 U0, we would still recommend you to redo the test after 3 years instead of 10 years, because that's a critical circuit, and you want to make sure that that circuit doesn't fail to work all of a sudden. Okay, now going away from tan delta, from partial discharge going to tan delta. First of all, the partial discharge test method is able to localize the fault. And the biggest difference between partial discharge and tan delta is with tan delta, and you see here at the very bottom, with 3D measurement, one cannot localize the weak point within a circuit. So tan delta will give you an overall value over the whole circuit and will just indicate the amount of deterioration or degradation from your insulation. So with tan delta you will not be able to localize the fault, but you will be able to prioritize replacement from aged circuits. So in an ideal world, we would see a cable as a pure capacitor without any losses, which is not always the case. Depending on the stage of the insulation, depending also on the age of the insulation, we will have some losses, and these losses are indicated by the tan delta value. Means the lower the losses, the better the shape of the insulation, and opposite, the higher the losses, the more deteriorated your insulation from this specific circuit will be. Now you see here some more explanation, the formula how to calculate tan delta. Basically what we measure, these losses here, basically that angle would be indicated as the tan delta value. So this angle would be an absolute number, and in the equivalent diagram, so the losses represented by the R, that would be our measured tan delta value. Probably the most important value you can achieve with tan delta measurement is the so-called tip-up factor. You see it here indicated in red. So on the scale here on this page, you see the tan delta value on this scale here. On this scale, at the bottom part, you see the applied voltage. In ideal world, we would have an independency from the tan delta value over voltage. So in this ideal world is shown here with this red line. So by ramping up the voltage, from 0.5 to U0 to 1.5 up to 2.5 U0, an ideal insulation would not show any tan delta dependency on the voltage. As already explained, the ideal world rarely exists, also in electrical testing not too much, but we see here various examples. If you see the yellow line or the green line, even the blue line, even though all these lines do show a certain dependency on tan delta value over voltage, we would still consider those values as being good and no need or no reason to action. But if you see something like that in the dark blue line, these would be for sure a moment where we need to action. That circuit would need to be either monitored very closely, or we would have to advise the maintenance team to exchange this circuit during the next plant outage. So to wrap it up, this tip-up factor is a very, very nice way to see the deterioration in your insulation in regard to tan delta value. Here, according to IEEE 400.2, there are some recommendations for you, what values are good, what are moderate, and when is a value bad enough that you need to action. And you see, this is separated between first series of cross-linked polyethylene cable with the abbreviation XLP, and now the modern type XLP cable, which are 3 retardant cross-linked polyethylene cable. You will see, and for time reason, let me check. I'll probably not go too much into detail, but here you see achieved result at U0 are considered to be good as long as they are below 0.1. Again, this is the tan delta values, or the losses, or which are representing the losses in your circuit. Further study is advised if at U0 your tangent delta is between 0.1 and 0.5, and action required if your tan delta value at rated voltage is higher than 0.5. If you compare these factors now with the 3 retardant cross-linked polyethylene, you will see that those values are significantly higher. So also here, by performing tangent delta value, you have to consider the type of insulation you are measuring. So here, instead of 0.1 as tangent delta value at U0, you would have here below 0.5 is considered as good. Further study is advised if your value is below 0.5 and 1. And last but not least, if your value is above 1, there is an action required. Okay, now coming to the equipment. What equipment do we have to address what I have mentioned before in the previous slide? So as an example, I have taken our TDM45 series. From a hardware point of view, it consists of 3 different items. And explaining you the item a bit more in detail, we have the base module, which is basically a sinusoidal waveform VLF equipment with the peak voltage of 45 kV, and it is meant for standard compliant withstand testing or pressure testing, as you may say, of short cable and dielectric loss measurement. So tan delta, with tan delta we are measuring the losses, and means within the TDM45 series of family we would be using the sinusoidal VLA form to detect these dielectric losses within your circuit. Then the middle part is the so-called boost module. It consists of a VLF booster, 40 kV RMS, not peak in this case, for standard compliant withstand testing of long cable, in contrary to short cable with the sinusoidal, up to 20 km of length at maximum test voltage. Then the last module is the partial discharge module, which we are using for PD diagnosis. It can either be used with the base module or it can be used with the booster. Okay, what is the wave shape of these different modules? So first of all, we have a sinusoidal waveform, positive power supply, negative power supply. In ideal case, VLF sinusoidal is at 0.1 Hz, and if you divide 1 over 0.1 gives you a cycle time of 10 seconds, means this cycle is equal to 10 seconds here. Also important to mention, as the voltage approaches the zero crossing during the discharge phase, the energy is systematically dissipated over a resistor as heat. So means we are losing all that energy and wasting the energy and burning it over a resistor. In contrary to that, we have the cosine rectangular, where we are using a resonance inductor to store the energy during the polarity change. That's the first big difference between VLF sinusoidal and VLF cosine rectangular. That's why we are able to test longer distance of cable with VLF cosine rectangular. You may know that the sinusoidal VLF units, they have the ability to decrease the frequency if the capacitive load is too high. So in ideal case, frequency would be 0.1 Hz, but it can be decreased up to 0.01 Hz. So if you have them 0.01 over 1 would give you a cycle time of 100 seconds for one cycle. The cosine rectangular doesn't have or doesn't need that ability to tune down the frequency. That means frequency at cosine rectangular is always 0.1, never ever any other frequency than 0.1 Hz. Now, to be able to do partial discharge measurement, we need a sinusoidal waveform, so the cosine rectangular would not enable us to do partial discharge test. So we have slightly modified the whole circuit that in the slope time, that means in the transition from negative to positive or vice versa from positive to negative, we have modified the circuit. You see here positive power supply, negative power supply, which is connected by the switch W. So in the slope process, we disconnect both power supplies, switches in neutral position, and we will close the switch S to allow the circuit to swing into resonance. And once it is swinging into resonance, we get the sinusoidal waveform, and this will allow us to perform partial discharge. The main advantage, and you will see that later on in the case studies, the main advantage of this modification of the cosine rectangular circuit is that we have a frequency which is between 20 and 400 Hz. while remember here we have a frequency at 0.1 in the best possible case or 0.01 in the least possible case, which means that the frequency applied to the device on the test, which is a cable, is between 500 and 5,000 times lower than nominal, and that will generate some problem. You will see that later on in the case study. While here with this modified cosine rectangular circuit, we have a frequency which is at the worst case 20 Hertz, which is 2.5 below nominal if nominal is 50 Hertz, or it is about 8 times higher if it is 400 Hertz. The frequency depends on the capacitive load, means the higher the capacitive load, the lower the frequency, and vice versa. But in any case, it's between 2.5 and 8 times away from nominal, but not 500 up to 5,000 times as it is with the sinusoidal 0.1 Hertz. Now, as an alternative to VLF sinusoidal and cosine rectangular, we have the so-called DAC testing. The reason why we have developed the DAC testing is the fact that a lot of cables, aged cables, they tend to break during testing, because pressure test means you apply 2.5 or up to 3 times U naught for 30 minutes or 60 minutes, and an aged cable could easily break during test, and people are a bit worried. So to address that, we have developed this DAC testing method, which is basically having just a negative power supply, but apart from this, the whole network is similar to the cosine rectangular. We charge the cable. Once it's charged, we short circuit the circuit, allow the system to swing into resonance, and during that we get a sinusoidal waveform which allow us to do a partial discharge test. So due to the very, very short ignition time from the cable on the test, which is a couple of milliseconds, or in the worst case a couple of seconds, there is no risk at all that you stress the cable in a way that it may fail during the testing. I've already mentioned it. Now, of course, if you have a system, once you did all the connection before you do a test, you want to make sure that all connections are done well, and therefore you do a calibration. With the calibration, you inject a known pulse, and you measure whether you are able to measure these known pulse. And here, as the far end must be open for PD measurement, we have here a positive reflection indicating the far end, which is an open loop, and that would be a perfect shape and would show us that all our system setup is done in a good way. Then operating software, up to a couple of years back, partial discharge has been seen as a very valid measurement to assess the severity of the degradation from your insulation system. But it has more been seen as a method made from technical nerds for technical nerds, because the interpretation and evaluation of the data required you to be an expert. This used to be valid, but is no longer valid. We have in our system, the TDM45, we have the expert being built in. So you see here on the upper scale from this diagram, you see the PD activity, the PD pulses, and these pulses are analyzed by an algorithm which is built in, and that algorithm automatically shows you where is your problem within your circuit. So in this example, we have a very short circuit of about 200 meters, and your problem is at around about 100 meters. So there's absolutely no need for interpretation or for evaluation. Everyone who can do the connection can run the test, can see where the problem is, and depending on the severity of the problem, you need then to action. But most important, you don't need to be the expert is built into our system. At the end of the test, with a simple mouse click, you get a report with all critical values being built in, which you can print out as a PDF on your computer, and we'll tell you all what is necessary to know whether this is a good circuit or whether that circuit needs further attention or needs action immediately. Now we have been talking about different wave shape, and it may be a bit confusing. So with that slide I tried to indicate what test can be done with what wave shape. So if we start here with VLS sinusoidal, you can see it is good to be used for partial discharge, it's good to be used for Tan delta, and it's good to be used for applied high voltage test or pressure test, as you may say. In contrary, the cosine rectangular is good to be used for partial discharge, cannot be used for Tan delta, and of course can be used for pressure test. The 50 Hz, which is not applicable, of course it's the same as 0.1 Hz. The damped AC is only used to do diagnostics test. So that may be a good indication for you if you're a bit confused about this different wave shape, what possible tests can be done by using different wave shapes. Here there are also different modules. It's pretty much the same as you have seen before. Different modules can be used for different testing, and I would not like to waste too much time on this. As said, you will get this presentation later on as a PDF file. But I would like to use some time on the case study because it's quite important and very significant. So case study number 1, we have been invited from a cable manufacturer, excuse me, and this cable manufacturer has invited 3 parties to run a test on a cable on a drum, and the customer has built in some weak points in that cable, and he wanted to see who is able to find these weak points. So what we have done here, we have been using the Centrix test one where a TDM45 is built in. That's pretty much the equipment which I tried to explain you before. Also important to mention is both our competitors could not find any fault, even not at higher test voltage, and you will see why this has happened. So here you see the fault built into the cable, and here you see the achieved results. Now here you see phase L1 has been tested by using the damped AC technology. Phase 2 has been tested by using the slope technology or cosine rectangular technology, and phase 3 has been tested by using the VLS sinusoidal. So you see here, first of all, before we apply high voltage, we want to know what is the natural existing noise at this specific location. And you see here quite a nice distribution on all the 3 phases. That's actually what you would like to see, you know, that you have an equal distribution of ground noise levels throughout the 3 phases. Now, most important is here you see cable energized with UNO, means rated voltage. We already see partial discharge, which is about almost 6 times higher than the natural noise level. 217 picocoulomb, that's with DAC. Phase L2, we see 171, which is a couple of factors above ground noise level by using the slope technology, and very, very interesting, using the sinusoidal waveform, no partial discharge at all. So you see that's the reason why the other 2 parties couldn't find any partial discharge, because they have both been using the VLS sinusoidal, and this is completely misleading, and I really want to highlight on this point. I'm not saying that the VLS sinusoidal is bad, it's just the technology which does not allow you to see the faults. Remember, VLS sinusoidal, we are using it ourselves, but we are recommended to use it for Tan delta and not for partial discharge, and that is for good reason, because if you invest your time and your money in doing preventive maintenance, you want to make sure that this preventive maintenance is giving you data which is reflecting the reality. And here we clearly see that it is not the case with all test methods. VLF sinusoidal shows you that this cable is in perfect condition, but we have seen on the picture before that cable is not at all in perfect condition, and this is clearly seen here with the slope technology as well as with the DAC technology. So you see we have then further increased to 1.7, where even the VLF sinusoidal has slowly shown some partial discharge, but far below the actual value and up to 2.0 knot. So how does it look like on a screen? You see here PD mapping for 1 U-knot, PD mapping for 1.3 U-knot, and PD mapping for 2 U-knot. So you see the blue color is DAC, amber is slope, and red is the sinusoidal. And you see only at the point of applying 2 U-knot, you slowly see a very, very small amount of partial discharge. But again, that partial discharge, the two other technologies have already seen at the rated voltage, which is applied voltage or U-knot. So again, the most important message here is, if you do preventive maintenance, make sure you do it with the appropriate technology. And these case studies clearly show what is appropriate and what is misleading. Now, going further, case study number 2, there was a request for a diagnostics measurement. This is the customer, cable details, and so on, year of installation and total length of cable. So that customer has called a services provider to perform some partial discharge, and he did that measurement on 11th of August, and he found 2 weak points within the cable. And these weak points have been reported to the network owner and saying that there are 2 weak points at 155 meter and 647, and we proposed to repair these joints. Then we further recommend to redo or repeat the PD measurement after the repair, just to make sure that these repairs have been done in a proper way. Now again, next measurement was of 7th of November, performed by the same company, and you see that on 155 meter the PD has not 100% disappeared, but at a much lower level. But however, on 650 meter we still see an issue. So the indication was that despite that the joint at 647 meter has been replaced, it is still not good. We still see much too much partial discharge for a new joint. And then the customer got a bit confused and thought, okay, I should have a second opinion, because I'm a bit frustrated, and I would like to get a second opinion. And the second opinion was done by a company using VLF 0.1 sinusoidal, and what a big surprise! All 3 phases do not show partial discharge, with the exception of phase 1, where you have here at about 900 meters some partial discharge. What you see here on this bar and this bar, this is the point of connection, that's the far end, and obviously the connection has not done in a PD-free way. That's why you have here elevated amount of partial discharge. So the conclusion here is that VLF 0.1 sinusoidal has only detected the weak spot at phase L1 at 980 meter. It could not show any imperfection in the insulation, and therefore we must say again, this measurement with using 0.1 sinusoidal waveform is not appropriate, because it is giving misleading information. Now, after all, customer has had a first opinion, has had a second opinion, and those both opinions are completely contradictory. So he got confused, and he asked himself which one is right and which one is wrong. So he asked then us to perform a measurement by using different wave shapes. So that measurement has then been done. So you see here the result. The first measurement has been done by using DAC on all three phases, and again, surprisingly enough, you could again see imperfection in the insulation at the same distance, about 155 and 649 meter. This is with DAC. By using VLF cosine rectangular, we could clearly identify the same imperfection at the same distances. And last but not least, we have been using VLF sinusoidal, and we couldn't see these weak points at all. Finally, after that, customer was convinced, that doing preventive maintenance means that you have to carefully choose the right waveform and the right equipment, that it is giving you the results which you want to get. And again, you want to see results which are reflecting the reality. And the indication is clear. DAC and slope technology are reflecting the reality, while sinusoidal VLF does not reflect the reality. Again, I'm not saying VLF sinusoidal is bad, because we are using it ourselves, but we are only using it for tangent delta because we found out that the results achieved are not reflecting the reality and are therefore kind of useless. Now, what is the summary? I believe my time is slowly running out. Summary of all this presentation is that the 60 Hz slope technology allows for the first time a standardized VLF measurement which can be accompanied by PD. VLF test is a pass-fail test, while PD will show you all the color codes in between black and white, means a pass and fail. Since you can do two tests at one time, it is of course saving your time and therefore saving your money. You have seen that the ability of testing high capacitive load is very limited with VLF sinusoidal, because it dissipates the energy over a resistor and burns it as heat, while we keep on using the energy with the VLF cosine rectangular, and we are therefore able to test much longer pieces of cable up to 20 kilometers. Most important, if we do the test either with the slope or the DAC technology, we see comparable results with nominal frequency. Nominal may be 50 Hz in some parts of the world and 60 Hz in other parts. In addition to that, we have also the so-called DAC technology, which is a non-destructive test, which is mainly recommended to be used on your H circuit, where you are worried that this test might fail if you apply to 5 or 3 times your knot. Also very important, there is no expertise required from you. The expert is delivered with the system, and the algorithm is automatically identifying the problem and is localizing these problems. So you don't need to be the specialist at all. It is already built in the system. So what are the conclusions? Conclusion is the combined voltage generation system, which consists of DAC and VLF cosine rectangular, allows diagnosis and withstand testing in one system and reflecting the reality. Cosine rectangular voltage wave shape is demonstrated as an excellent excitation voltage for PD testing. It reflects the reality. That's very important. VLF cosine rectangular test voltage will allow PD monitored withstand testing on longer cables or 3-phase cable, that you can run the test parallel on all 3 phases at one time, which is of course extremely time saving and therefore also very cost effective. And also very important, if you are asked, what is the main difference between Tan delta and PD, I try to highlight it here. Tan delta is an overall indication about the total insulation from the whole circuit under test, while PD is a very effective measurement to find the weak spots within a circuit. So Tan delta, we recommend to use it to prioritize the exchange of your aged circuit, because it just indicates the health index from your total insulation from the circuit under test, but it does not allow you to localize faults. While partial discharge is a very effective and easy to use measurement to be able to find the imperfection within the circuit under test. Okay, almost at the end, I would like to use that opportunity to say a special thank you to Mr. Doble-Megger. Philip is an application specialist based in our German facility, and he's doing a lot of PD and TD tests, and thanks to him I could use his PowerPoint presentation, and I just had to compile his slides in a way which suited me, and that has really saved a lot of time. Thanks once again, Philip, fantastic work. Now we are at the end with this presentation, and as said, very happy to answer your question right now, or should you prefer to raise your question later on by email, you're most welcome to do it at any stage later on. Thank you so much and have a great